These are now open empirical questions that can be investigated through advanced microscopy and biophysical experiments. While the shielding hypothesis remains controversial and is, honestly, far from proven, it provides a plausible, if speculative, path forward. It suggests that we really shouldn't dismiss the possibility of quantum computation in the brain based on simplified models alone. The intense debate over decoherence in the brain really highlights a fundamental difficulty. Biology is messy. When testing a theory like OR, which combines a claim about fundamental physics, objective reduction, with a claim about biology, namely quantum processes in microtubules, a negative result is always ambiguous. If our mass invariance test fails to show a frequency shift, does it mean the physics of OR is wrong? Or does it simply mean that decoherence is too strong in microtubules and the biological part of the theory is wrong? It would be immensely valuable to find a way to test Penrose's physical prediction, the gravity-induced collapse, in a clean, controllable system completely separate from the complexities of the brain. And, actually, this is precisely what physicists in the field of optomechanics are now attempting to do. They are designing experiments to probe the boundaries between the quantum and classical worlds using non-biological systems. The goal is to create and sustain a quantum superposition of a macroscopic object, an object large enough for its gravitational self-energy to be significant, and then watch to see if it collapses on its own, just as Penrose predicts. If they can demonstrate that tau equals h bar divided by Eg holds true in a vacuum chamber on a lab bench, it would lend tremendous credibility to the physical foundation of the OR theory, regardless of whether it ultimately happens in the brain. These experiments often involve using lasers to trap and cool a tiny object, such as a nanoparticle or a microscopic mirror, down to near absolute zero. By cooling it, they remove the thermal vibrations that would cause decoherence. By trapping it in a vacuum, they isolate it from collisions with air molecules. Once the object is perfectly still and isolated, the next step is to use quantum tricks to place it into a spatial superposition, a state of being in two different locations at once. The separation distance might be tiny, maybe only the width of an atom, but for an object containing billions of atoms, this is a massive superposition with a significant gravitational self-energy, e.g. The stage is then set for the crucial measurement. According to standard quantum mechanics, this superposition should last indefinitely as long as it is isolated. But according to Penrose's objective reduction, it has a finite lifetime, tau, determined by its mass and separation. The experiment is designed to hold the superposition and simply wait, watching for the moment it spontaneously collapses. By repeating this with objects of different masses and different separation distances, physicists can check if the collapse time scales exactly as the Penrose equation predicts. This provides a direct, biology-free test of the core physical claim that underpins the entire quantum consciousness hypothesis. Let's imagine one such tabletop experiment in more detail. A team of physicists uses a focused laser beam and optical tweezer to levitate a tiny silica nanosphere, about 100 nanometers in diameter, inside an ultra-high vacuum chamber. They use other lasers to cool the sphere's motion until it is almost perfectly still, reaching a quantum ground state.